In part 2 of the carbon cycle, we'll look at the inorganic carbon cycle. This involves diffusion across the ocean-atmosphere boundary, the solubility pump, the long-term inorganic carbon cycle, which has components of weathering and also carbonate metamorphism, and also negative feedbacks on that long-term cycle. Recap from part 1 of our carbon cycle talks. Organic weathering is artificially sped up by fossil fuel burning, leading to a long-term increase in CO2 today and a decrease in oxygen. Also, the biological pump allows for a transfer of CO2 in the surface ocean to the deep ocean. The exchange, however, between the ocean and the atmosphere happens by diffusion, which is a physical process. So we need to understand how this works. Solubility depends on temperature. Solubility is how well or how easily something can be dissolved, for example, CO2. CO2 is more soluble in colder water. For example, a warm Coke gets flat more quickly than a cold Coke. Why is that? Because more CO2 can remain dissolved in the colder soda. So when pressure is released from a cold versus warm can, it comes out of solution more so in the warm can than the cold. In other words, the warm can has more bubbles escaping from the solution. So in other words, the CO2 in there was more soluble in the cold Coke. Same for the ocean. Colder ocean can store more CO2 in general. What if the ocean warms up? It releases more CO2 because it's less soluble and it has to outgas it just like the warm Coke did. Diffusion. Gas at high concentration spreads into regions with low concentration. Einstein's famous for showing the diffusion of gas in a vacuum can be expressed as the coefficient of diffusion times the concentration difference. So in general, what this means is if you have a high concentration of gas somewhere next to an area with lower concentration, there will be a general flux of that gas from higher to lower concentrations trying to mix it out, make it reach equilibrium. How this works with carbon in the oceans. CO2 will diffuse from the ocean to the atmosphere if the ocean's CO2 concentration is higher than that of the overlying atmosphere. CO2 will diffuse from the atmosphere to the ocean if the atmosphere's CO2 concentration is higher than the local oceanic waters. You have to consider, however, both the temperature of the waters, because cold water can hold more CO2 in solution, and the amount of CO2 in between them, in other words, the partial pressure difference between them, before you can calculate the CO2 flux between the atmosphere and the ocean. One equation that summarizes this is that the flux between the atmosphere and the ocean is equal to some transfer coefficient, K, which depends on a number of things, but also depends on winds, times the solubility of water, S, times the difference in partial pressures of CO2 in the ocean and the air. So why does K depend on the winds? Well, a number of ways it depends on the winds. The first easiest way to think about it, as the winds hit the surface of the ocean, it roughens up the surface, makes waves. That increases the surface area where you can exchange gases across. You have to also consider that the wind can help mix the surface layer in the ocean down to the depths, bringing up new water, which might have less CO2 in it and is able to accept more CO2 than the water that was there before. It can do the same thing to actually the atmospheric layer. So the wind has a big play in this exchange as well as the partial pressure difference. Looking at oceanic temperature in general and then looking at CO2, so now we can look back at the Vostok ice core 420,000 years back. CO2 is the purple line here, going up and down every about 100,000 years, pretty well in tune with atmospheric temperatures as inferred from the isotopic composition of water in the ice cores. You see a nice correlation over time. So the question is, was it more CO2, stronger greenhouse effect, so Earth warmed, or did it go the other way? Was there warmer temperature, so the oceans warmed up and outgassed just like the warmer soda did, and so that raised CO2. So which is the cause and which is the effect? It's actually not 100% clear on these long time scales who's leading who, but it appears today that the CO2 increases from fossil fuel burning is leading the temperature changes. So question, so what you want for the surface ocean to take up CO2 is cold water that has little CO2 in it already. Because you want a large partial pressure difference, you want the atmosphere to be loaded with CO2, the oceanic water not to have much, but also be cold. That's going to give you the most flux from atmosphere to ocean. Where would be the best place to find these waters? Well, the equatorial upwelling zones are cold, but they're going to be rich in CO2 from the biological pump. The coastal upwelling zones in the Pacific are also going to be rich in CO2 because they're coming from depths which has high CO2 amounts. Same thing for the center of the subpolar gyres. In the center of the subtropical gyres, you have Ekman transport converging old surface water, which is relatively warm, so that's not going to give you the best case scenario here. However, in the polar waters that are about to sink to depth, that's where you have the best ratio. So these polar waters are cold, they don't have a lot of CO2 because they haven't been upwelled recently, so they can accept by solubility a lot of CO2 from the atmosphere. Here we're looking at a modeling effort, looking at the amount of anthropogenic carbon, so carbon produced from fossil fuel burning, in total water columns in the ocean. As you can see from this modeling effort, most is entering the ocean in the cold North Atlantic where this cold water is sinking. This is what's called the solubility pump, where that cold water recently cooled as it went along the coast here and just about to sink is really accepting a lot of atmospheric CO2 here, a lot of which is anthropogenic coming off the coast of the US. And so it can accept it by solubility and then sink it into the deep oceans, and it starts to run down at depths towards the equator following the deep water circulation. So this concept of abiotic, not involving biology, exchange of atmospheric CO2 with dissolved oceanic CO2 by that concentration difference primarily is called the solubility pump. Water with less CO2 than atmosphere will take CO2 in. Water high in CO2 will give CO2 to the atmosphere. So in general, this graph is showing upwelling, which brings up a lot of CO2 that was pumped there by the biology, comes to the surface, rich in CO2, will flux to the atmosphere in general because the concentration gradient's going that way. However, during deep water formation, they're going to have more atmospheric CO2 than the cold surface water there, so there'll be a flux from the atmosphere to the ocean, which will take it down to depths. On the left here is a graph of partial pressure difference between the atmosphere and the ocean. Red values here show where the ocean surface water has a lot more CO2 than the overlying atmosphere, and blues and greens show where the oceans have less CO2 than the overlying atmosphere. So that's just the partial pressure difference. However, calculating the actual flux into and out of the ocean, you can see Takahashi here in 2002 did that calculation, and you can see that it spatially agrees with this very well, which means that the concentration difference really helps control the flux of CO2 between the ocean and the atmosphere. Looking at Takahashi's graph a little bit closer, reds here are fluxes out of the ocean. Here we're showing the zone of equatorial upwelling, so that's going to bring CO2-rich water from the depths to the surface. So of course it's going to flux out of the ocean to the atmosphere. Same thing in the subpolar gyre up here by the Aleutians. This is also a nice upwelling zone off the eastern coast of Africa. And then there's places where the flux is going into the ocean, primarily places with lots of winds and waves, and also recently cooled water. This water comes up on the Kuroshio Current up past Japan, starts to get cool here, but it hasn't been upwelled recently, so therefore it doesn't have much CO2, so you're allowed to get a flux from the atmosphere to the ocean if the concentration gradient's going that way. Same type of effect here in the Southern Ocean, where you have cold water that has not been upwelled recently, able to accept atmospheric CO2. So now putting this together, the atmosphere-ocean flux is driven by diffusion. It depends on the difference in partial pressure or concentration and the oceanic temperatures. However, it's up to the biological pump to sink the oceanic CO2 at the surface to depth so that more CO2 can be pumped into the upper ocean. So diffusion between the atmosphere-ocean interface and the biological pump are very much connected. So let's try to visualize how this might work. Take some atmospheric CO2 and push it into the surface ocean, the first blue container here on the left, by a diffusion process. Then the biological pump could remove that CO2 and sink it to depth by its methods. Once it's in the deep ocean, two things can happen. First of all, it could get upwelled, which would really effectively push it back into the surface ocean, so perhaps I should have drawn another arrow here, bringing it back to the left tank. Or it could get buried, meaning that not all the CO2 in the deep ocean gets upwelled. Some component of it gets buried in organic sediments, and that's important too. So this is like the atmosphere, upper ocean, lower ocean exchange. The atmosphere-ocean flux can only continue if there's a removal of CO2 from the upper ocean by that biological pump. Looking at the net CO2 flux between the atmosphere and ocean today, we find that at present, since we have increased atmospheric CO2 so much, there's a net flux of CO2 going into the oceans. More CO2 going in the oceans than is leaving. So 92 gigatons per year enter the oceans, only 90 gigatons per year come out, And so the net exchange is 2 gigatons per year going into the ocean on annual global mean. And this again is because we've changed the concentration gradient between the atmosphere and the ocean. So now in general, more atmospheric CO2 moves into the ocean every year than vice versa. So the ocean is helping to absorb a lot of that extra CO2 right now that was piling up in our atmosphere. But what is the cost of that? And the cost of that is really ocean acidification, which is something we'll look at in the next few lectures. So looking at a more short-term budget of where is the atmospheric CO2 going in the short term today, we emit about 9.1 gigatons of carbon a year. Of that, 7.6 is from fossil fuels, and 1.6 gigatons is from deforestation, which removes the sink but also adds decomposition, which increases CO2 in the atmosphere. So those emissions are shown in the upper graph here. This is petagrams of carbon, but it's the same thing as gigatons of carbon per year. So they're showing land use over time, how much has it contributed, a fraction of what the fossil fuel contributed, but not so small as to be ignored. And so those have increased over time. So we know that our sources of anthropogenic carbon have increased over time. Then you can ask, where is it all going? Well, 4.1 gigatons per year are accumulating in the atmosphere, raising CO2 as evidence from the Mauna Loa record. 2.2 gigatons of the year went into the oceans, which is causing acidification, is something we'll look at. And then 2.8 gigatons per year are accumulating both in the forests and also in the soils. And this graph on the lower right is showing those sinks. The atmosphere has been accumulating, taking up more and more CO2 over time. The land has definitely some fluctuations that we'll look into, very interesting fluctuations, but it's taking more and more over time. In general, the oceans are taking in their part of the CO2 as well. To be complete, we'll take a look at the long-term inorganic carbon cycle briefly. The weathering of types of inorganic rocks, including silicates and carbonates, removes CO2 from the atmosphere ultimately, whereas weathering of organics that we looked at already tends to add CO2 to the atmosphere. So it gets quite complicated, but there's silicate rocks out there, of which we have many, that when you do weather them with CO2 that's dissolved in rainwater, the ultimate process is to remove 2 molecules of CO2. The products run into the ocean, where animals use the products to make shells. During the shell-making process, 1 CO2 is gained by the surface ocean, which can readily flux to the atmosphere through diffusion. You're still missing 1 CO2 molecule, and it's incorporated, at least the carbon part of it's incorporated into a shell itself. And of course, it doesn't look like this shell, but just to make the point, those shells become incorporated in sedimentary rocks where plate tectonics will move them to subduction zones where they're acted on by volcanism, and ultimately this process will give you the CO2 back to the atmosphere. And so this cycle is very long, 10 million years or longer, to have a full balance between CO2 removed from the atmosphere and CO2 gained back to the atmosphere. So there's negative feedback loops associated with that weathering loop. The part of the loop that involves the plate tectonics, that's mostly a function of what's happening in the interior of the Earth, but the part that happens outside in the atmosphere, in other words, the weathering rates, is definitely a function of surface temperatures and CO2, so let's look how that works. Let's say the surface temperature increases somehow. If that happens, silicate weathering rates automatically go up, and that's simply because those chemical reactions happen faster with higher temperatures, more energy in the system. So surface temperature goes up, the weathering rates go up, atmospheric CO2 goes down since that weathering draws down CO2. That draws down the greenhouse effect, which returns your surface temperature to some more normal temperature. In other words, it reduced that anomalously high surface temperature. The other part of the loop that's interesting, if surface temperatures go up somehow, that increases evaporation globally, which ultimately will increase rainfall globally. Since you have more atmospheric water vapor in the air to create rainfall from, if rainfall rates increase, you're going to get more weathering, more rain on rock. That draws down CO2, draws down the greenhouse effect, brings your temperature back down. So another stabilizing effect. So these stabilizing effects are negative feedbacks that are active on tens of millions of years. So they become important when you're looking at very long timescale climate. Now we looked at plate tectonics very briefly, so let's have a return of that. What happens with plate tectonics and what ultimately pushes the world's plates into motion is mantle convection. The outer core is a really hot place. That heats up part of the mantle, which makes it less dense than mantle around it and causes it to become positively buoyant. It starts to rise up. ultimately will touch the crust, dump a lot of its heat, which cools it back down, makes it more dense, and it sinks back, completing a convection cell. So these convection cells have this orientation in places where there's a lot of upwelling. And so you have a lot of new material coming out in spots, specifically what are called mid-oceanic ridges. And so this drives new material in between these plates, but at the same time, the plates are actually floating and getting pushed by the mantle convection itself, so spreading apart, what's called seafloor spreading. So this is ultimately what drives plate tectonics itself, this process. So interestingly, this is why the oceans and why the mid-oceanic ridges are in the middle of the oceans. Consider the Rift Valley in Africa right now. It is a place where the plates are spreading. Over time, millions and millions of years, that will continue to spread, and as it does, there'll be a gaping hole left where those plates spread apart. Ocean will fill in that, and ultimately a new ocean will form in that region. The Red Sea is an example of this process, where those plates underneath there are also spreading, and the Red Sea is a relatively new sea that will grow over time, over millions and millions of years. A more mature area would be the Atlantic or the Pacific, any of the large oceans, where there is a mid-oceanic ridge, pushing apart the plates. Again, that's what formed the ocean, having those plates spread out. So as new seafloor is extruded, the continents are pushed away from that rift, creating an ocean left in the gap. So again, this is a process that is actually driving plates apart. So what happens when other plates hit each other? In other words, they converge in what's called convergent plate boundaries. There's three primary types of collision when these plates meet. You can have continental plates meet each other. You can have a continental plate meet an oceanic plate, or two oceanic plates meet each other. Now in general, the continental plates are thicker and also less dense than the oceanic plates. They're formed out of quite different rock over time. So let's look at the first one. When two continental plates collide, one of them may be less dense for a variety of reasons. So when they hit, though, they tend to buckle, creating mountains. Mountains are formed, for example, the Himalayas form this way. The rise of the Himalayas we'll look at changed weather and climate patterns and actually increased a lot of weathering. If a continental plate hits an oceanic plate, the continental plate being less dense than the oceanic plate is always going to stay at the top while the oceanic plate will dive underneath, shown here in what's called the subduction zone. So the oceanic plate being more dense and thinner gets pushed underneath. It drags a bunch of organics down here that helps create magma, and you can get volcanic regions bubbling out underneath the continental plate as a result. An example of this would be the Pacific Northwest. All their volcanoes, or their ancient volcanoes, are owed from this process. Two oceanic plates can collide too, and again, they're both pretty dense, but one of them will typically be less dense than the other. The plate that's actually oldest will be the coolest and therefore the most dense, and so the oldest plate in these collisions will tend to subduct underneath the relatively newer plate. So if this happens, two oceanic plates collide, one gets dragged under, again can form magma. After a lot of time, you can form volcanic islands as that grows to the surface. An example of this would be Japan. So plate tectonics and weathering, there's times when plate tectonics moved mountains into rainy regions. For example, when the Himalayas were born. This led to a decrease in CO2 for quite some time, millions and millions of years, due to lots of this inorganic weathering, which reduces CO2 on very, very long time scales. After a whole lot of time, the products of the weathering would form sedimentary layers. Again, those shells will start forming sedimentary layers that someday get pushed into subduction zones, returning the CO2 to the atmosphere. This would ultimately lead to a long-term increase in CO2 as those carbon-rich layers are cooked by volcanoes. So these processes, they're important over 100+ million years time scales, but today these processes are relatively unimportant. What is important is the burning of fossil fuels and the speed up of the organic weathering that we looked at in previous lectures. This graph summarizes some of the things we talked about in this lecture. We have this physical weathering of silicate rocks. It's really a chemical weathering. The products go into the ocean. You start to form carbonate marine sediments. The seafloor spreads due to the mantle convection. It can push those sedimentary rocks into subduction zones, which can get cooked up in volcanoes, returning CO2 to the atmosphere. So these are all things that are very important on very long time scales. Key points from this lecture for the inorganic carbon cycle: the diffusion of CO2 between the atmosphere and the ocean depends on the concentrations in each reservoir. The biology plays a part here in removing CO2 from surface water and sinking it to ocean depths. Currently, the atmospheric CO2 is rising so fast from fossil fuel usage that there's a net uptake by the oceans, and we'll look at the consequences of that with an ocean acidification talk soon. The weathering of rocks, weathering of inorganic rocks, specifically silicates, removes CO2 from the atmosphere on very, very long timescales and builds sedimentary deposits on the ocean floor. Subduction of these deposits will ultimately force the CO2 back out through volcanic seeps. So while the subduction rates depend on processes in Earth's interior and plate tectonics, the weathering rates are very sensitive to the amounts of atmospheric CO2, and we think that this has provided a mostly stabilizing effect of atmospheric CO2 on geologic timescales.